Hello guys. Welcome to our 6th lesson. In this lesson, we are going to improve our last robot, which we already built in a previous lesson. To be more precise, we are going to use our joypad or game controller to move this robot around the 3-axis. If you remember, we had one rotation around this axis, a continuous rotation in this case. Then, we had a revolution around this axis, a rotation limited in its range. Then we have a translation, defined as a prismatic joint around those axes. The black part here is the drilling unit, which can move or translate along the beam. Okay, so now we want to be able to move this robot, not using the sliders, but using a simple game controller, which you plug into your computer. Before starting this lesson, we have to make sure that we have the following packages installed on our system. First, we have to install the package ROS, then your ROS version, probably Humble or Galactic, followed by TF transformations. So, this package must be installed on your computer, otherwise, you cannot implement the code. The second package PIP3 transforms 3D. Please install those packages if you don't have already. Once they're installed, you can start writing the code and implementing your robot. By the way, remember that when using a gamepad to control a robot, like in this case, you have always to close this window because otherwise, it conflicts with the data coming from the game controller. For instance, this window is telling now the robot to go to the position 065, which is an angle in radians. But using the game controller at the same time, the game controller can send another value here. This situation generates a conflict, since you have two input sources. In this case, you see that the robot is moving very quickly between two different positions. So in order to avoid any problem, close this window when using a game controller. So, now let's start. For this lesson, I decided to write already the code and explain it to you step by step. So, now from our workspace, we need to go on our package source. In this case, the package was called Tolima. Let's navigate into it and from there into the folder with the same name. So again, Tolima. In this folder, you can see that I added a new file, which is robot code.py. The other file, joystick test, contains the code we developed in the last lesson. Since we don't need the joystick test file anymore, we could theoretically remove it or ignore it. Now, let's open the file robot code.py. Let's see what we have here. As usual, we start importing ROS. That means that we import node from the package rclpy. Then, we import the quaternion package and vector3 from geometry message. Sometimes it can be useful to import vector3 as well, but in this lesson, you can remove it completely, if you prefer. Then, we import joy and joint state from the sensor message package. Why joy? Because joy is the message that our joystick constantly updates with the inputs from the joystick every time I have the joy node running. So, let's take a look to the joy topic and see how the message is composed. Let's type ROS2 run joy node. The second topic from above is the joystick topic. Connecting a gamepad to the computer and running this topic, you can see that we have two fields, 6 different axes and many different buttons. Since we need to grab those input values, we need to import the joy package into our code. Then, we can use them to move our robot. Now let's open the URDF model of our robot, which we defined in the previous lessons. In order to move the robot, we need a joint state message. So we import the joint state message into our code. Furthermore, we import from the package TF-ROS2 the methods transform stamped in transform broadcaster into our code. Those packages are mandatory when the robot is no fixed, but it can move its basis around. The reason will be clear in a few minutes. For the moment, let's import those packages in our code. As usual, we start by writing our main routine. The syntax and the code here is identical to previous examples. Again, we pass no arguments to main. We initialize the ROS node at first. Then, we create an instance of our robot class, which is going to be defined by us above. By the way, please note that in this case I'm going to use a try except block, because when I use Ctrl-C, a keyboard interruption, to stop my program, I want this exception branch to be executed. This line is going to be printed and my instance is going to be destroyed. Lately, we exited the code. Now, let's go and see how to use our joystick inside our class. We start by defining the robot class. We pass the parent class node and then, we define at the beginning of the class an initialization method or constructor. Then, we call super and we pass to its constructor the name of our node. Now, we define three different things here. First, we need to define a new broadcaster or publisher, which is going to publish the absolute position of the robot. What does it mean? We have here a base link frame that you can see here, which is connected to this black part. And then we have a ODM frame, which is fixed to the grid, which represents the outside world. We need now to define this broadcaster in this way, because our robot is no more fixed in space. But it can move. We are going to flip over this robot and move it around the X and the Y axis. Second, we create a second publisher for the joint state message. This publisher is going to publish the position of the joints over the topic joint states. In this robot, we have a rotation around this axis, then another rotation around this axis, and lately a translation along the beam. Third, we need a subscription to the joystick node. The joy node is still running in the background, as you can see on this terminal. That's all. Now let's define some attributes to store the first position of the robot. Self X for the X position, starting at 0. Self Y for the Y position, starting from 0. Self Z for the position of the head unit of the drilling unit. Then, we have self theta for the first angle. Self phi for the second angle. Self psi for the last angle. So now, we define a new transformation message. Probably, this is the most important part of this tutorial. We define it with using the message transform stamped. This message is completely different from the message joint state for many reasons. In this message, you see that we define ODM as the first frame, anchor to the world, then we define baselink as the first robot frame. The transformation between those two frames is no more inside the URDF file, because it is not a joint frame transformation. In fact, there is no ODM frame in the URDF file. Let's open for a moment the URDF file. In the first URDF file we edited, there was the following line, link name ODM. Now, we get rid of it, and we remove it completely. So the first link, in this case, is base link. Going back to the code, we have ODM as the header frame, and then we have baselink as a child link. Looking into the Global Options menu, you can see that there is no ODM frame yet. There, you can find ARM1, ARM2, baselink and drilling unit. They are exactly as defined in the URDF file. Now, let's define the joint state message as a new attribute for this class. In there, I define the name of any single joint. So in this case, base ARM1, ARM1, ARM2, and lately head. Remember, those names are exactly the names that you used to define the joints inside your URDF file. This means that base ARM1, ARM1, ARM2, head are the name of the joints and they must match exactly the names in this list. No change allowed. So then we define self Q, which is the quaternion transformation for 3D rotations in space. We pass Euler angles in radians to the method quaternion from Euler, and we get a quaternion containing this transformation. Quaternion are mathematical objects, very efficient from a programming point of view. Since we want to flip the robot of 180 degrees around the x-axis, we type np pi 0, 0. If you pass 0 as first argument, then the robot will just stay in the same orientation as seen before. Last but not least, we define a getLogger, outputting the status of the robot when running the code. Now make sure your joystick node is still running in the background. In our getJoystickInput method, we pass the joystick message as argument. So every time a message is broadcasted over the topic joy, this callback is executed. Why? Because the getJoystickInput method is passed to the joystick subscriber at line 26. Every time the topic joy is updated with a new joystick input value, the code inside the now implemented method is executed. MSG is the message containing the information about the joystick. So, I just add this position information to the already created self-x attribute. Changing self-x changes the position of the robot. The value 0.06 is just a scaling factor. If I would write 1.0, then the changes will be too big and the robot would literally jump too much. All those units are in meter and moving the joystick a little bit means huge steps for the robot. So I want just to reduce the changes by using a scaling factor. You can even try the values 0.1 or 0.05. It depends only on your finger sensitivity. For the y position, we take the second value in our list axes. But how to determine which index? Just start the joy topic in a terminal and start counting from 0. As you can see, every time I move my joystick, for instance, towards right, then the first element, index 0, changes to -1. On the other side, moving the same joystick to the left, I get plus 1.0. If I want now to have the second value for the y-axis, then I must use index 1 and assign it to the self-y attribute. Pushing the joystick down, I get the value -1.0 at the index 5. Pushing it up, I get the value 1.0. It is always up to you which axis should be mapped and which can be ignored. On the right side of my joystick, and moving that stick left, right, up and down, I change the values in the axis with the index 2 and 3. In my case, I assign them to the rotation parts of my robot, psi and theta. Pay always attention to the units of your position and orientation attributes. Since psi, pi, and theta are in radians, you do not need any scaling factor, since radians represent very small movements. In this case, I assign the number 2 to the theta and the number 3 to psi. So every time a new message is retrieved over the joy topic, this part of the code is going to run. The single input values are then stored in the attributes I created in the class constructor. Just for simplicity, I created a second method in my robot class, which duty is to broadcast all the transformations. This means that the method broadcast transformations is now called. In this new method, we need to update the timestamp of the transformed stamp and the joint messages. So, first we use the ROS method getClockNow to message and store it in the new attribute timeNow. Then I update the timestamp of the self-odom trans message. Remember, we defined self-odom trans above inside this class as a message of type transform stamped. Once the timestamp is updated, we need to update the x, the y, and the z values. Pay attention here. The z coordinate is not 0, but 5.0. The reason is that I want to put my robot at a height of 5.0 meters from the ground. You even try another value. You can even put to 0 if you want. This is only the starting coordinate of the robot, and it is not going to be changed during the execution of the code. In our example, we deal not only with translations, but even with rotations. Rotations in ROS are expressed as quaternions. For this reason, we create a new quaternion object passing the arguments self q0, self q1, self q2, self q3. Self q is already a quaternion. We created it before for expressing the robot rotation around its x-axis. Basically, we rotate the robot upside down. For this reason we wrote np pi. If you would put 0, then the robot remains in its actual position. Putting pi, the robot is going to flip over of about 180 degrees around the x-axis. You can try different values, and then you understand exactly what is the effect on your robot. Next is the very important step. Please take care of this line, because now, we are going to broadcast the transformation over the network using ROS. We need this send transform method. Self-ODM broadcaster was the already defined publisher for this transformation. It was defined at the very beginning of the class. To the send transform method, we pass the attribute self-ODM trans. Now, it's time to update the joints positions. First, we update the timestamp in the header of the message. Then, we update the single value in the field position, exactly as in our previous tutorial about joint state messages. To the joint values belong theta, psi, and z. Last, we publish the new joint state message. Now let's update our setup.py file, which is needed for the package compilation. TestJoy is no more needed. We add a new program, Tolima equal Tolima robot code :main. Again, this is the name of the program. This is the name of the package, this is the name of the file, and this is the name of the main routine. Once done, we need to update our package XML file. You need to add the following dependencies: RCLPY, the sensor messages, the geometry messages, and TF2 ROS transformation. Okay, let's go now to our workspace directory, and let's compile the new code. It did compile. After sourcing the install directory, we need to execute ROS2 run Tolima. The status message is running. You see there is a frame above the robot. This is the new frame, ODM. This frame is exactly 5.0 meters above the ground. Now, I'm using my joystick to move my robot around. Moving the joystick along X and Y, I can move the robot around. The other joystick used for rotations works as well. Let's rotate it around this axis, it works. I'm trying to find a better perspective. Now, I want to rotate the beam around this axis here, and it works. Sometimes there are some artifacts, which make the CALADA file not visualizing correctly, but it depends mostly on your graphic card. Now let's move the drilling unit. Yeah. It's moving forward and backwards. I can stop the drilling unit and then move it back. Now, back to the code. The most important thing in this case, or in similar robot configurations, is that you have two transformations. One transformation is between the ODM frame and the baselink frame. ODM trans is the message that you have to send in order to move your robot in your virtual world or environment. The second transformation is the joint state message, as we saw already in the previous tutorial. Once you have updated the joint state message, you have to publish it as well. So, in total, you have 2 messages, and not only one. Self-odom trans must be sent. And self-joint state must be sent. If you send only once, then your robot is not going to move properly. Okay, it was enough for this lesson. Practice, practice, practice. Practice is the best way to learn. Please try different configurations. You can even try with a completely different robot. Thank you very much for your attention. See you in the next lesson. Bye.